Okay, so we continue with the discussion we have had on parametric oscillation. What we had discussed last time, what is called a singly resonant oscillator. Remember, we had this crystal here. There are two mirrors on either side. This is the length of the crystal here. So I launch a high energy pump wave, omega p, and assume that the crystal satisfies this phase matching condition corresponding to a pair of frequencies, omega s and omega I. This or the corresponding quasi phase matching condition. In a singly resonant oscillator, the reflectivity of the mirrors at the signal frequency is quite high, while at the pump frequency and the idler frequency, Rs, Rp and Ri, they are close to 0. That means the pump wave gets transmitted through the crystal, the idler wave also escapes from the cavity, while the signal is trapped within the cavity by mirrors of reflectivities R1 and R2. And these are close to 1. These are high reflectivity mirrors. So because it is a resonant cavity for only the signal, only one of the frequencies between signal and idler, is called singly resonant oscillator. So what we found out is that because of this cavity, the signal frequency should form standing waves inside the cavity. So that determines the frequencies omega s that are possible to exist within the cavity. So once omega p and omega s get fixed, omega I also gets fixed. We also calculated what is the threshold power or threshold pump intensity required for overcoming the losses in the cavity. And that tells me what kind of power levels I need to feed in at the pump frequency for the oscillation to begin. When the losses at the signal frequency inside the cavity are exactly compensated by the gain provided by the parametric amplification process, the signal then oscillates continuously within the cavity and I get a coherent source of light at signal frequency. This is omega p coming out and newly generated omega s coming out. If the two reflectivities are unequal or not equal to 1, neither of them equal to 1, I have signal coming out from both sides. And of course, the idler is escaping the cavity. We also saw the relative bandwidths, the amplification bandwidth, the intermode spacing, and the width of each mode. So, if you make a singly resonant oscillator cavity, and if you pump with a corresponding pump here, ensure that the cavity satisfies the conditions for phase matching and the energy conservation, then you get the oscillations begin as soon as you reach threshold pump power. So actually what you are converting is from omega p to omega s, and the laser coming out, the coherent source at omega s is by drawing energy from omega p. And as I mentioned before, when you start to draw a lot of energy from omega s, I can't use the original equations where I assumed no pump depletion. I need to solve all the equations simultaneously. I need to consider the fact that the electric field at the pump will also decay within the cavity because of conversion to omega s. So this is a singly resonant oscillator, and as I showed you earlier also, I can tune this oscillator by changing the pairs of frequencies at which phase matching condition is satisfied. So if you rotate the crystal, for example, suppose their mirrors were not touching the cavity, they were outside, so I could actually rotate the crystal within the cavity or the direction of propagation of the pump within the cavity. So I could have a situation like this, for example. I have a mirror here, I have a mirror here, and I have the crystal separately inside. So I could actually rotate the crystal within the cavity, change the angle of propagation of the pump with respect to the optic axis within the crystal, and use birefringence phase matching to pick up pairs of frequencies omega s, omega I, where I will satisfy the phase matching condition and the oscillation condition. So as I rotate my crystal here, the frequency coming out from here, omega s frequency coming out, will change for a fixed omega p. Because the frequency of maximum gain will change, because as you rotate the crystal using birefringence phase matching, the frequency pair omega s omega I, which satisfies both these equations, will change. And so I will be able to tune the oscillator. I can do that, or I can change the temperature of the crystal, which will change the refractive indices and hence change this condition, or I can do other things. So it is a tunable oscillator, and you can actually tune it over a very large range of wavelengths. You are not using any energy levels, unlike a laser based on population inversion, and hence there's a huge tunability that's possible in such an oscillator. We also estimated the powers required. 15 watts, 20 watts of power is required to start the laser, to start this coherent source. So the other oscillator, which we will discuss today, is the doubly resonant oscillator, DRO. Here, what you have is, you have the same geometry again. Let me assume the crystal is filling the cavity. I have a mirror here, a mirror here. This is the length of the cavity. I again launch a pump from here. Now what I have is Rp is equal to 0, Rp is equal to 0, Rs is equal to R1. Let me assume the two mirrors have the same reflectivity, and Ri is equal to R2. Let me keep it Rs, okay. Rs, let me, this is close to 1, this is close to 1, and this is Ri close to 1, Ri is also close to 1. The two reflectivities are equal. I'm assuming a special case where the two reflectivities are equal. I could have different reflectivities, but let me assume the energy reflectivity at the signal frequency for both mirrors are almost equal and equal to Rs, which is close to 1. Similarly, the reflectivities of the mirrors at the idler frequencies are Ri and both close to 1. So in this case, what's going to happen is now both the signal and the idler will form standing wave patterns inside the cavity. The signal generated inside the cavity and the idler generated inside the cavity will oscillate back and forth within the cavity, forming a standing wave pattern inside the cavity. And because I'm resonating both the signal and the idler within the cavity, this is called a doubly resonant oscillator. So what are the conditions I need to satisfy for omega s and omega I? First thing is omega p is equal to omega s plus omega I. Kp is equal to Ks plus Ki. And then resonant mode. So what will be the values of omega s? We had calculated last time. M times pi c by ns into L. M is an integer. Similarly, omega I also has to satisfy a similar condition with a different integer. So let me go p pi c by ni into L. In the singly resonant oscillator, the second equation was not there. There was no condition on omega I. So in addition to omega s being resonant inside the cavity, I also have to have a condition that omega I, which are allowed inside the cavity, are only these. And please note that because ns and na are different, the frequency spacing of the signal and idler frequencies are different. And I will show you later on this leads to a lot of problems in the instability of the cavity. Okay, so let me assume I can find a set of omega s omega I which satisfies all these four equations. So what will happen is, when I launch omega p into the cavity, I will first generate spontaneously down-converted photons. Because of these two conditions being satisfied, there will be a pair of photons omega s omega I over a certain range. Remember that even if delta k is not equal to 0, there is a finite probability of there is an amplification or there is a generation that takes place. Now, out of those frequencies which are generated, the noise generated, those frequencies which satisfies these conditions also will then start to resonate inside the cavity and increase in energy. So what will happen is, I will have a strong signal and a strong idler coming out of the cavity, two frequencies coming out, which satisfy, the pair satisfies all these four equations simultaneously. Now, our objective now is to find out what is the power or what is the intensity required at the pump frequency to satisfy the condition that the overall gain becomes equal to overall loss. That means in one round trip, what is the loss suffered, the net loss suffered by the beam must be equal to, the net loss must be 0. There must be no loss. The gain must compensate the loss. There is loss because as the signal bounces back and forth, it loses a certain fraction. 1 minus Rs here and 1 minus Rs here. The idler loses 1 minus Ri and 1 minus Ri here. And so, the inside the cavity, the energy in one round trip gets reduced because of finite transmission of the mirrors, but it gets amplified because of parametric amplification process. And when the amplification gain, when the gain becomes equal to loss, I reach threshold and the oscillation will start. Now, I have, in the SRO case, remember, I did not write any equation for the idler. Now I can't do that. I have to write the complete equation. So, remember, what we had done was we had solved the equations for the general case. So you see, when you write the condition, remember here that at the starting point, there is both ES and EI. Both ES and EI propagate over a length L. Both ES and EI get reflected, propagate back. Both ES and EI get reflected, and that is one round trip. So, when the beam goes from the left mirror to the right mirror, there is amplification. And that amplification will now depend on both ES and EI. The initial conditions for my amplification problem is now ES at 0 is not equal to 0 and EI at 0 is not also equal to 0. So, let me recall the two equations we had derived earlier. So, if you have this situation like this, so this is Z is equal to 0, this is Z is equal to L. So, ES at Z, at some value of Z, is actually ES at 0 cos hyperbolic GZ plus I times square root of omega S Ni by omega I Ns EI 0 star sine hyperbolic GZ, and EI star of Z is equal to minus I under root omega I Ns by omega S Ni ES 0 sine hyperbolic GZ plus EI 0 star cos hyperbolic GZ. G is the gain coefficient. G square is kappa S kappa I mod EP square. Again, these equations have been written under no pump depletion approximation. So, to calculate threshold, I can use this pair of equations because just at threshold, the conversion is below threshold, the conversion is not very efficient. At threshold, after threshold, of course, the conversion is very efficient. You generate a lot of signal and idler from the pump, but the threshold calculation, I can assume that I can estimate the threshold by assuming no pump depletion. The earlier SRO case was when EI 0 is equal to 0, so you can already see that ES sub Z is given by ES 0 cos hyperbolic GZ, which is what we had used. And remember, this also assumes delta K is equal to 0. Complete phase matching. Because otherwise I have some of the coefficients inside the hyperbolic functions and the solutions are different. The gain coefficient is less if you get out of phase matching. So, this is the ES and EI star at any value of Z given ES and EI star at Z is equal to 0. So, now the problem becomes very simple. Let me write this equation as follows. Let me write this as ES of Z, EI star of Z is equal to cos hyperbolic GZ I times square root of omega S Ni by omega I Ns sine hyperbolic GZ minus I square root of omega I Ns by omega S Ni sine hyperbolic gz, then you have cos hyperbolic gz into Es of 0, Ei star of 0. I have written this pair of equations in a matrix form. Okay, so let me call this some ABCD. A, B, C, where A is cos hyperbolic gz, B is this coefficient here, C is this quantity, and D is cos hyperbolic gz. So this matrix, ABCD matrix, actually connects the signal-Reidler pair electric fields at Z and Z equals 0. Now, how do I write a matrix for reflection? So this is the matrix representing transmission from the plane Z equals 0 to Z equals L. Please remember, for one round trip, what I need to do is start with a pair of Es and Ei here, propagate from Z is equal to 0 to L, let it reflect, propagate from Z is equal to L to Z is equal to 0, let it reflect, and I get a pair of Es and Ei star. And one round trip represents this entire process. And the Es Ei star that I get after one round trip must be equal to the one which I started with. Then I will have an oscillation condition, threshold condition. So this matrix represents the change in Es and Ei star as it goes from here to here. Now what about the reflection? How do I represent in terms of reflection, the matrix in terms of reflection? So for example, let me write, suppose I want to write Es reflected and Ei star reflected in terms of a matrix, and Es incident and Ei star incident. I am assuming that the mirrors do not introduce any phase changes. Please remember, in writing these equations, I have assumed that the mirrors do not introduce any phase changes. Okay, this is only the propagation phase change. So the mirrors are assumed to be mirrors which do not give any phase changes, but they only reflect with the energy reflection coefficients of Rs and Ri. So what is the matrix I must use? Root Rs 0, 0, because Es reflected is root Rs times Es incident, Ei star reflected is root Ri times Ei star incident. This is assuming no phase change. Otherwise, I would have had exponential I phi s and I phi I sitting here. Okay. And what is the matrix? So this is the matrix in going from left to right. What is the matrix in going from right to left? So what matrix? Same means? No. No. This is reflection matrix. So I start from, okay, I start from Z is equal to 0. At Z is equal to L, I will obtain by multiplying the field here, field pair here by this matrix. Then I will get the reflected wave by multiplying by this matrix. Then the wave propagates from this mirror to this mirror. So what is the matrix? If there is no change, unit matrix. Okay, and then another reflection, which is the same as this, because I am assuming the mirrors to be identical. So I can actually complete one round trip. So what will happen is, let me write this as, so Es after one round trip, Ei star after one round trip is equal to, so this will be root Rs 0, 0 root Ri into a unit matrix into root Rs 0, 0 root Ri into A, B, C, D matrix into Es 0, Ei star. RT is round trip, one round trip. So this is starting, this is propagation from left to right, reflection by the mirror, propagation from right to left, reflection by the mirror. So if I open this up, the product of these two is simply RS00 Ri. So I will have RSA and then RSB, RIA, is that right? Sorry, C and D. I'm sorry, yeah, C and D. So what is the condition I impose now? No, my condition is this must be equal. This need not be unit matrix. This has to be equal to this. What is my condition? That the signal and idler fields after one round trip must repeat themselves. So this ES after one round trip and EI star after one round trip must be equal to ES 0 and EI star of 0. I'll get an equation, right? Let me substitute here. So I will get an equation which is simply RSA, RSB, RIC, RID into ES 0, EI star of 0 minus ES 0, EI star of 0 is equal to 0. So this is nothing but RSA minus 1, RSB, RIC, RID minus 1 into ES 0, EI star of 0 is equal to 0. Because this is unit matrix into this quantity. So actually this equation is simply this. So next, what do I do? For a non-trivial solution, the determinant of this equation, this matrix must be 0. So I get a condition that determinant of RSA minus 1, RSB, RIC, RID minus 1 must be equal to 0. So let me leave this simplification to you. You have expressions for A, B, C and D. So what you will get is the following. Cos hyperbolic G threshold L is equal to 1 plus okay, in ABCD, I need to use Z is equal to L. Remember, this is any Z. This ABCD, which appears here, has Z is equal to L in the equation. Because I propagate from left to right over a length L. The crystal has a length L. And I'm assuming here that the crystal fills the entire cavity. If it does not happen, the gain will be only happening in a part of the cavity. Please remember, if the situation is like this, the gain happens only in this part of the cavity. So that length L which appears here must be this length only. And the frequencies are determined by this entire length. And the refractive index of the crystal and the refractive index outside, everything, okay. So please be careful that you need to calculate properly the frequencies of oscillation, and this amplification will only depend on the length of the crystal, not the length of the cavity. In my example which I am considering, the cavity is equal to the length of the cavity equal to the length of the crystal. The crystal is filling the entire cavity. Otherwise, this length L is the length of the crystal within the cavity. Okay, if you put Ri is equal to 0, you essentially get back the old expression that we had. Okay. Now again, Rs and Ri are usually very close to unity. So this is almost close to unity, 1 plus 1 by 2. Okay, so this is almost close to unity. So I can again make an expansion of cos hyperbolic function, and I get the following expression for G threshold. This is assuming, approximately, this is assuming that the reflection coefficients at the Sigler and Idler are very close to unity. Otherwise, this is the expression. I can approximate this equation provided the Sigler and Idler reflection coefficients are close to unity, and I get an expression for this. So, can you tell me what is the ratio of this? So, G threshold doubly resonant oscillator to G threshold singly resonant oscillator. What is the ratio? Let me write here 1 minus Rs into 1 minus Ri by L. And what was the G threshold as SRO? Singly resonant oscillator. We had done last time. Under root 2 or 2?
No, under root. 1 by.
Okay.
1 by root 2.
So root 2 comes in the numerator because this G threshold is in the denominator. Okay. Give me the numerator. L by?
L by root 2 into 1 upon.
So into 1 upon under root of R1 R2 minus 1 raised to power minus 1.
So in denominator only. 1 by root R1 R2. Yes. 1 by
Put R1 is equal to R2 is equal to Rs.
Okay.
Because there are both mirrors have the same reflectivity equal to Rs. So what do I get?
R by root 2.
Rs is close to 1. So I'm neglecting that Rs. Okay. Is this right?
No, in the numerator also. Upon R.
No, Rs is equal to 1, I am assuming. That Rs I am neglecting because Rs is close to 1. I am throwing away that Rs. Is this right?
Yes.
Then it should come 1. Why?
Is this right?
Sir, are we assuming?
Okay. Yeah, but close to 1, but I can't make it 0. See, I am making a factor Rs, I am just putting it at 1. But 1 minus Rs is close to 0. So I can't put it at 0 and then I get 0. So obviously I know that the threshold G for DRO is not 0. Okay. Now, from here, can I estimate the ratio of the intensities required for the DRO and the SRO? What is G threshold? What is G given by? Remember, G square is kappa S kappa I mod P square. So this is kappa S kappa I. So IP is equal to NP by 2C mu 0 mod EP square. So this into 2C mu 0 by NP into IP. So IP is proportional to G square. And this ratio is in terms of, so IP threshold DRO by IP threshold SRO will be equal to G threshold dr square DRO by G threshold square SRO, which is equal to 1 minus Ri by. Okay. Now, if Ri is close to 1, say Ri if I take as 98% reflection, if Ri is close to 0.98, this ratio becomes, if I call this R, it's a ratio, R, not R, some ratio T. So, T becomes 0.01. The threshold intensity required are a factor of 100 down. So, we are talking of maybe 10 watts there. So, it's 100 milliwatts here, 100 times down. And that is very interesting because then you don't need so much power, and you can almost have a continuous wave oscillation of these parametric oscillators. So, a doubly resonant oscillator requires much lower powers to operate than a singly resonant oscillator, because here both the signal and idler are having high intensity within the cavity, and both of them are responsible for drawing energy from the pump. And so, to start, you need much lower threshold pump powers for a doubly resonant oscillator as compared to a singly resonant oscillator. Yeah.
So if the threshold pump powers of doubly resonant oscillator is low, and we are assuming that no pump depletion approximation for.
So, I cannot use no pump depletion approximation to calculate the signal and idler powers coming out. But as I mentioned, I am neglecting pump depletion only to estimate the threshold value. Because I know just before threshold the depletion is very little, just above threshold there is a strong depletion. So, I am approximating the position of the threshold by assuming a no pump depletion approximation and calculating the threshold. So, this gives me an estimate, a very good estimate of the threshold pump power required to start the oscillator. Okay, now let me try to show you schematically what the problem is in terms of stability of this oscillator. Now, let me go back to those equations which we have written requiring the standing wave at the signal and idler frequencies. Remember these two equations. So, let me write them again here. So, omega s must be m pi c by nsl, and omega I is equal to p pi c by nil. Now, I am assuming omega s is greater than omega I. The signal frequency is higher than the idler frequency. So, now from here, delta omega s is approximately pi c by nsl, and delta omega I is approximately pi c by nil. I am writing approximately because please remember ns and ni are also functions of frequency. I am neglecting that frequency dependence in writing this equation. Otherwise, I must take into account the fact that if omega s changes, ns also changes significantly. So, I am neglecting that. So, which is larger, omega s, delta omega s, or delta omega I? So, is ns larger or ni larger? As the frequency increases, refractive index increases. So, ns is bigger than ni. So, delta omega s is less than delta omega I. Frequency spacings are not the same. Now, let me draw you a figure which sort of shows this problem because of this condition. Okay, here is a figure which is a very interesting figure which I draw. Please remember that the sum of these two frequencies must be omega p. Okay.
Then they should be equal. Delta omega s and delta omega I. Or has it to become
no. Delta omega need not be, spacing need not be the same. No? This is spacing. Okay. So, now what I draw is a figure like this. Omega s increases in this direction, and omega I increases in this direction. such that at any value, the sum of these two is constant. Let's note this figure. The axes are reverse of each other. So the sum of these two values is the same as the sum of these two values, the same as sum of these two values. I can have a scale which is increasing in this direction in one and increasing in the other direction in the other scale. Okay? These two figures have scales such that omega s plus omega I at any value is omega p. Now, in this figure, let me draw the lines corresponding to this omega s and this omega I. Remembering that the spacings are given by these and that delta omega s is less than delta omega I. So first let me draw, for example, the spacing here. Some arbitrary number let me draw. Let me pull this up here. Okay, so the way I have drawn this figure is the spacing delta omega s is one of these squares. Now please note that because of this condition, it's like a vernier. Because suppose, let me assume that this is a value of omega I, where this is the value of omega p and omega s omega I, where I satisfy this condition, both of this. Suppose this is delta omega s, delta omega I is larger. So the next one will not appear here, it will appear somewhere here. The next allowed omega I frequency is not on this line corresponding to this omega s, slightly different. So what will happen is this come here, then here, then here, then here, 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 and again matched. Right? It's like a vernier. You see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9 divisions, and 1, 2, 3, 4, 5, 6, 7, 8 divisions. So there is a match here, and there is a match here. So either this pair will oscillate, or this pair will oscillate. These pairs cannot oscillate because corresponding to the omega s, there is no corresponding omega I which can form a standing wave pattern inside the cavity. So either this pair will oscillate, or if not, then this pair has to oscillate. Or there will be another pair coming like this. Every range of frequencies, there will be a pair of frequencies which will satisfy both these conditions simultaneously. That creates a problem, because suppose for some reason temperature changes or length changes, both move, both these combs move, because refractive index depends on temperature, or the omega s and omega I values depend on temperature, on the length of the cavity. Any fluctuation in the length of the cavity or the temperature is going to move both these combs. And what will happen is the oscillator will adjust itself to a pair of frequencies which satisfy the condition that they are exactly overlapping. Both frequencies must be allowed in the cavity. So what is actually happening is there are too many constraints on the pair of frequencies, omega s and omega I. As I written here, there are too many constraints. And this leads to problems of instability of the oscillator. If you suddenly see one pair of frequencies coming, suddenly that shifts to some other pair, and then it shifts back to another pair. It keeps on fluctuating randomly, because depending on the fluctuations in the cavity, the pairs which satisfy the condition that the sum of these two equal to omega p, phase matching condition, and also that they are both modes of the cavity, is putting too much constraints on the frequency pair, and this leads to a lot of instability in the parametric oscillator. So DROs are by nature not very stable. So you need to take very extensive, you need to put extensive efforts to make the cavity as stable as possible. This does not happen in a singly resonant oscillator because you need to satisfy only one of these conditions. Yeah?
So in case we have, L is not the same for the both of them. Like we make such that the L is different for idler and signals. So we have delta omega is equal to delta omega, and this probably will not be there.
No, but you see, please remember that it depends also on NS and NI, which are functions of frequency. So they're not uniformly spaced actually. The way I've written here, for the small delta omegas, I have assumed these are frequency independent. But even if you choose this different lengths here, Ns and Ni will be frequency dependent, and I will not be exactly able to match at every frequency both the combs. This can lead to a problem. But of course, maybe if I choose different cavity lengths, which means I must put another mirror here outside. And because the frequencies, well, I don't know what kind of different lengths are required. And then if the mirrors are not precisely satisfying the condition of zero reflectivity at certain wavelengths, you will form another standing wave pattern cavity inside. So you will have 3 cavities now interacting with each other. So you will have a situation like this. You have 1, 2, and 3. So there is one mirror here, another mirror here, another mirror here. So signal will be oscillating like this, iter will be oscillating like this, but there is another cavity sitting here in between, which can lead to problems. Okay, so these are coupled cavity systems. So there are people who do coupled cavities, but I don't know whether that can resolve some of these issues. Okay, so a DRO has this problem, but as you can see here, the DRO has a much lower threshold requirement than compared to a singly resonant oscillator, and it is very interesting from that point of view. Okay, so with this we will finish discussion on the second order nonlinear effects. So if you have any questions on the entire topic of second order nonlinear effects, we can have a short discussion right now. Otherwise, I will introduce to you the next higher order nonlinear effect, and which we will discuss not in detail but briefly before we move on to the quantum mechanical interpretations of the processes. Anything that you would like to ask or raise? Okay, so what we have essentially seen using second order effects, we have second harmonic generation. We generate twice the frequency. Then we looked at the reverse process of generating omega from 2 omega. And I showed you that classically that is an impossible process, but it does take place, and that is a quantum mechanical explanation for it. At the same time, if I launch omega and 2 omega simultaneously, I can amplify or attenuate the omega frequency, and this is a phase sensitive parametric amplifier. So the energy can either transfer from omega to 2 omega or 2 omega to omega depending on the phase of the two inputs at the input of the crystal. We then shifted on to a process in which the 3 waves are all having different frequencies, omega p, omega s, omega I. So I can use this. So that's the most general. Second harmonic generation is a special case of this, where I have omega s is equal to omega I, but I can have all 3 frequencies are different. So I can use this process, a 3-wave mixing process, these are all 3-wave mixing processes, to generate some frequency by launching omega s and omega I, or difference frequency by launching omega p and omega s. And the difference frequency generation process I showed you leads to an amplification of the signal. So I can have, in this case, I can have either phase insensitive amplification by launching omega p and omega s only, or a phase sensitive amplification if I launch all the 3 waves simultaneously. And this phase sensitive amplification is very interesting, because I will show you later on in quantum mechanical analysis that this can lead to very interesting output from these amplifiers. And once we have an amplifier for a frequency here, we can actually put that inside a cavity, an optical cavity, which is a pair of mirrors, and convert the amplifier to an oscillator, and that's the optical parametric oscillator. And so these are commercially available devices, OPOs, which can be used for tuning over a broad range of wavelengths, primarily in infrared. And these are, many of them are pulsed parametric oscillators, where the pump is not a continuous wave, but a pulse wave. And we have not discussed the pulsed operation of these lasers or of these oscillators. But what we have seen essentially is that what are the conditions needed for the oscillation to begin, what kind of pump levels are required, what kind of pump power levels are required for crossing the threshold, and when will the oscillation start. And the most interesting aspect of this OPOs is the tunability, where you can actually tune the frequency of oscillation, because it's a nonlinear process and not dependent on the energy levels of the atomic system. There is no absorption here. This is a parametric process where there is no absorption. Unlike a laser built on population inversion, a pump frequency is absorbed, energy is absorbed, the atoms go from one level to another level, then they drop down to the 3rd level somewhere, which is the metastable level, and then there is a population inversion generated, and then there is amplification. So there is an energy loss in this cavity here, because you're losing some energy of the pump when the atoms transmit from one level to another level. This is a completely parametric process where in principle there is no energy loss. If you neglect all the other scattering losses, this is a system in which the incident energy is equal to output energy. And you can have very interesting properties of these amplifiers based on nonlinear processes. Okay, so we'll just spend a few minutes in the next topic, which is third order nonlinear effects. If you recall, we had written P is equal to epsilon 0 chi E plus 2 epsilon 0 d E square plus epsilon 0 chi 3 E cube, and so on. I'm writing a scalar equation just for simplicity. This is the linear part. These are the second order nonlinear effects proportional to E square. This is the third order nonlinear effects proportional to E cube. This one is present only in crystals which do not possess a center of inversion symmetry. So if you take a medium like glass, which is a completely random matrix, this coefficient is absent. So the first nonlinear term that comes in is epsilon 0 chi 3 E cube, and those are responsible for third order effects. What I will show you is some of these effects are automatically phase matched. That means the nonlinear polarization and the wave it is trying to generate are actually traveling at the same speed. They're automatically phase matched. Some of these processes need you to take steps to phase match them. You can build amplifiers based on this, just like you can build amplifiers based on this. These are also called parametric amplifiers. This particular one, actually I'll show you, leads to what is called as an intensity dependent refractive index. The refractive index of a medium starts to depend on the intensity of the light wave because of this E cube term. And this effect leads to applications in all optical switching, where you can switch light from one port to another by using nonlinear optical effects and so on. So this is a very interesting effect. And this particular term is extremely important. It has been studied widely because of optical fiber communication. Optical fibers are used in communication. They are based on glass, silica glass, and this is not present. This is the nonlinear term that comes into picture. And this leads to, just like other nonlinear term, it leads to mixing of light at different frequencies. If you launch light at 2 frequencies, you will start to generate new frequencies if you satisfy phase matching conditions. So it starts to generate new frequencies, and that creates a problem because at those new frequencies, you may be actually having a communication going on. So if you launch omega 1, omega 2, and omega 3, the waves at omega 1 and omega 2 can mix together to create omega 3. So the person who is using omega 3 to communicate will start to have crosstalk from omega 1 and omega 2, the other two people who are talking. So this is a serious problem in communication, and so people have found a method to reduce this effect of this, and that is by killing phase matching. If you ensure that there is no phase matching, this process becomes very weak, and you sort of gain in that process. I can actually use this phase matching to use this process to generate new frequencies. So actually this nonlinear effect can be used for amplification or for generating new frequencies, or it can play havoc in systems in which you don't want nonlinear effects. And that happens primarily in communication systems where, because light waves are propagating through 1,000 kilometers of fiber. So that's a 1,000 kilometer length is a huge length in which these nonlinear effects keep on building up. And they lead to problems. And one of the methods, which I'll briefly discuss, is to destroy phase matching. And once you destroy that, the efficiency goes down significantly and you have almost gotten rid of the problem. Of course, some of them you still are not able to get rid of them. Okay? So I think we'll stop here. So next time what we will do is we'll start to analyze the effects of this term We will not spend too many lectures on this, but some brief discussion, and then we will move on to quantum mechanical analysis. Okay, thank you.